And while we're doing the laptop swap, I'd love to welcome our next speaker. So Sylvain Calinon is a senior research scientist at the IDIAP Research Institute in Switzerland, and also a lecturer at EPFL, where he researches things including optimal control, geometrical approaches, and HRI. In particular, he's recently worked on learning representations for manipulation planning. And today we'll be talking to us about learning manipulation policies from humans for problems and settings where there are discrete and continuous constraints, exactly of the sort we look at in traditional game problems.
All right, thank you very much. Let me know if you see my screen and if you can hear me well.
Yes, we can hear and see you.
Okay, excellent, excellent. So I'll start on if it doesn't work, yeah, let me know. So yeah, so first, thanks very much for the introduction. And I'm sorry I could not join in person in Atlanta, so I had to cancel my trip. I would have preferred to do it there instead of doing that remotely. So I come from IDIAP. It's a research institute in the Swiss Alps. It's about 300 persons working in the field of machine learning. The institute exists for more than 30 years. So for us, AI is not new, a new topic, but it's really something that we have been doing from the beginning. It's affiliated with EPFL. And at IDIAP, I'm heading a group called Robot Learning on Interaction. So first, I will show a few examples of manipulation skills that we are tackling in our group as examples of typical experiments that we conduct in our group. So the first one is about deciding when to use tools in order to manipulate objects. So we have like an optimization problem with both discrete and continuous variables, with discrete decision variables that is when on which object to pick, on which tool to pick in order to facilitate the manipulation. And we like also to think of the robot as whole body manipulators, so not necessarily thinking of the end effector, but also thinking of the full body. And this is particularly useful if we want to transport objects that are bulky, and if we want to use the forearms of the robot to do so. This is for prehensile manipulation, but non-prehensile manipulations are also very helpful if we want to sort objects, if we want to push a bulk of objects, if we want to separate objects in order to better grasp them, or more generally, to use the environment in order to help at manipulating the objects by using in this video like a wall in order to tilt an object more conveniently and then pulling it back to a desired configuration. From time to time, we also participate in challenges. And here, one that I wanted to highlight is this Aerokey challenge that happened at NeurIPS in 2023. That was also requiring to tackle task and motion planning problems by considering both discrete and continuous variables. Discrete for the strategy to use, and obviously continuous variables here is very important to be tackled in a very fast way in order to compete with this kind of challenges. I have another slide showing other kind of non-prehensile manipulation related to throwing and catching that also need to be very fast. And another example with precise insertion, where here we don't only need to manipulate an object, but we also need to decide how to actively sense the environment. And this is again like a decision variables to take if we want to have better precision by using like active sensing techniques. So together with non-prehensile manipulation, we are also interested in aspects of shared control and teleoperation. Here I show the example of an experiment we did in the context of the Dexroth project that was about remote manipulation of valves as a shared control paradigm. And the video below is showing what we did in the lab in order to understand what are the problems behind this shared control paradigm and how to use one of the robots as an input device in order to replicate the movement to another robot that is viewed as the remote robot, and how to handle the different the different mapping that you have between the two in the location of the valves. So that's an overview about the experiments that we do in the group. And we do that with machine learning. But when we say machine learning, nowadays, it means deep learning. And the problem we have on our side is that we like to think of this problem as learning, but we like to think of these as frugal learning problems. So we are not considering learning by passively observing a huge amount of data. We are instead considering learning as an interaction process, as having the human in the loop. The human can be here to discuss about the task, to put names or semantics on what needs to be done. So we need this way of communicating between the robot and the user, and to talk about aspects of the task that the robot has to learn. So the way we see the problem is it's a scaffolding problem. So scaffolding is a term being used as a metaphor to say that at the beginning we need a lot of support in order to construct something. In the case of a house, we need a lot of scaffolds. And when the house is being built, then we can progressively remove the scaffolds, meaning that the house is standing on its own after we have built this knowledge. For a robot, it's a bit the same. We need the user at the beginning quite often, but progressively, once the robot has understood a few concepts of the task, then we can progressively lower the scaffolds, and ideally, we would like the robot to then become autonomous when it has mastered the skill. We also like the meta learning problem of combining different learning strategies. And typically, how to combine self-refinement mechanisms together with imitation learning mechanisms. And when we talk about this, if we think about an interaction with the user, then it's good to think about frugal learning problem in our view. Because frugal means here two things. It means first that we would like to learn with only few amount of demonstrations, if we talk about an interaction that is to provide demonstrations to the robot. But we also mean frugal by what needs to be learned, in the sense that we have quite a lot of models and prior knowledge that we can inject to the system, and it would not be efficient if the robot would learn that if we know exactly how to do it. So if we have some kind of prior knowledge, if we have some kind of inductive bias that we can inject to the system, then we should do it in our view in order to have robots that can acquire skills in an efficient way. So the technique that I wanted to discuss more specifically with you today, it's something called tensor networks. So all of you know about neural networks. Maybe fewer of you know about tensor networks. It's a technique used in physics. We can also think of it as a processing pipeline involving some architecture in the same way as a neural network will involve some architecture. Here, the architecture is quite different. It's often simpler, but it fits very well with this frugal learning aspect. It's basically trying to find a low-rank representation of our data, where the data doesn't need to be stored as a vector or as matrices, but the data can be higher order data arrays, so can be tensors. And there are a lot of structures like this. So I will stop here at the most simple one that is called tensor train, and I will show you what we tried with this tensor trains technique. So first, we're using tensor train to encode a cost function, or more conveniently, we encode actually a probability distribution. So tensor train is in some way a model, like a model allowing us to encode probability distributions. Then the variables of interest can be both task variables or policy variables or variables related to plans or trajectories. And we can have environment variables related to the situation that the robot is encountering. So when we want, after having learned this distribution, if we want to regenerate some new behaviors, what we will typically need is some form of conditional sampling, in the sense that the environment is giving us the ongoing situation, and then we would like to have some action or some policy in order to do some task. And by doing conditional sampling, we can find what's the action that would give us a high score or a low cost to do this. And here, TensorTrain is a good structure to do that because it's allowing to use a simulator offline in order to approximate this distribution. And then online, we can do conditional sampling in a very fast way. So let me try to give you in just a few minutes some kind of like a short introduction about what it does, like more of an intuition about what it does. And for this intuition, I will use only 2D data, while in reality, we have this higher order tensor. So with 2D data, we have an iterative process that will sample like points in this array and evaluate this point with a simulator. But it will do that in a very smart way by using what is called cross-approximation. And with this cross-approximation, it will iterate along the different dimensions and find the dimensions, like what looks promising in each of these dimensions, in order to determine what to do next. And in this process, we are actually building a low-rank approximation of the distribution. If it's rank 1, we cannot do much. It's finding only one solution. But if it's more than rank 1, then we can actually rebuild distributions that have multiple peaks. So we can really model a multimodal distribution that will allow us to generate multiple options for the same task to be fulfilled. So that's in 2D. So in 2D, it looks like that. In 2D, it's not super interesting because the number of points that we had to test is quite high. But the bigger is your tensor, the less you can make we can take good samples because it's a huge amount of space. So here, this TensorTrain factorization is allowing to make trials that are smart in order to build this underlying tensor distribution. So that's what is called TensorTrain. So now for task on motion planning, why do we care? We care about that because with this technique, we encode both discrete and continuous variables. When we have continuous variables, what we actually do with this variable is that we generate an histogram. So we discretize this variable, so that all variables will actually be discrete. Then discretizing a continuous variable, sometimes the problem is you lose resolution capability. But what's happening in practice is that we use this tensor factorization technique as a way to provide warm start to local solvers. So even if we have this discretization for the continuous variables, what's happening in practice is we give an initial point that is very close to a good candidate, and then we couple these TensorTrain factorization techniques to some Newton methods or some gradient methods. And this coupling is very efficient because the TensorTrain is acting globally, so it's a global optimization problem that is then refined by a local optimization problem. And we tested that with various kinds of tasks involving trajectory optimization, task on motion planning, and always showing what kind of variations it can generate. If I'm taking the example in the middle, it's showing a pick and place trajectory, but it's displaying multiple options that we have to satisfy this same pick and place trajectory where we have given as input the picking location and the placing location. Okay, so now how to have the user in the loop? So how can we use this kind of algorithms, but also having some kind of guidance from the user? So with this algorithm, as I told you before, it's an algorithm that is selecting dimension by dimension which one look most promising. So we can do that as a self-refinement mechanism, so as a reinforcement learning technique. But we can also have the user specifying these entries. And what is kind of interesting here is that if we encode both environment variable and policy variables, it means that we have different learning strategies that can be considered. For example, if the user is providing, here there is a typo, if the user is providing policy variables, it means we have a learning from demonstration technique. So it means instead of having the robot trying different policies, it's the user showing the policy to do for a given situation. But if the user is specifying environment variable, it's becoming a scaffolding technique. So it's some kind of guidance where it's still like reinforcement learning, but we have the user like in the loop to tell to the robot, try this, try that, try to solve this challenge instead of this one. And it's a structure that is facilitating this meta-learning problem of combining these different learning strategies together with the human in the loop. Then one of the aspects of encoding that in a discrete way, so first it's good for task and motion planning because when we have like symbolic variables, we can encode these symbolic variables in the tensor and we can learn the relationships between these symbolic variables and the continuous ones. And also, like if they are described in an intuitive way, then we have also the semantic description that we can exploit in order to communicate with the user. So we didn't do much at this stage, but we believe that this kind of tensor networks techniques can be very useful for this. Now, I will show you a few extensions of that. So what I showed before was called tensor train for global optimization. Now, we were encoding, in this case, the full cost function. Like we had a cost function. We were really taking that as I would say, standard optimization problem, taking the complete cost function and trying to solve that as a global optimization problem. But this encoding strategy can also be used to encode other kinds of functions. It doesn't need to be the complete cost functions. It can also be the intermediary functions that you need in a problem. And typically, it can be value functions, it can be advantage functions, or I would argue any other kind of functions that can be described in a probabilistic way. So we have a series of work that is extending this tensor train for global optimization to dynamic programming, and in particular with the view that this can be used as a reinforcement learning techniques. And here I'm showing the work mainly from Tang, who first used this approach as a way to encode value functions in a problem requiring both discrete and continuous variables. Here in this case, the continuous variables were manifolds. So he wanted to combine different manifolds and to understand how to switch between these manifolds. So the switching aspect is the discrete variable to tackle. And on a manifold, like finding a geodesic would typically be the continuous variable to optimize. And in his first approach, he was exploiting the low-rank factorization to do that in an efficient way by combining this with a symbolic search. So in this work, he was first trying like to just use together a symbolic search algorithm together with this low-rank factorization technique. And currently, we are also investigating how the symbolic search can also be represented by a tensor train. Because if you think of a tree that would have the same amount of branches for each node, like this tree, we can also represent that as a tensor. And it means that we can make a low-rank factorization of this tree in order to determine what are the most promising paths along this tree. So we noticed that if we use that, so if we use these tensor train low-rank factorization techniques together with standard Monte Carlo tree search, then we could speed up, importantly, what the Monte Carlo tree search algorithm could do. So it's like a coupling that works very well. In the same way as for TTGO, the coupling between tensor train and Newton's method for local refinement was working very well. Here, we also realized that the coupling between Monte Carlo tree search and tensor train was very promising. So we're currently testing that. It's a work in progress. We recently find this. We first tested that with pushing tasks involving switching of the face of the object that we use for the pushing. We have been also testing that with the bimanual manipulation of bulky objects. And in this case, it was a task requiring this bulky object to first be rotated before being lifted. And in our early result, we compare this approach of combining Monte Carlo research and TensorTrain together with our previous approach, TensorTrain for global optimization. Also comparing this to Monte Carlo research, but without the low-rank factorization, and also with CMAES, that would be another alternative to do this task. And these early results are showing that we have very promising results in this direction. So to conclude, as a summary, I wanted to highlight three different things. So TensorTrain and tensor networks are promising models that we should consider more carefully in robotics. They allow to encode both continuous and discrete variables, which is an advantage for TAMP. They can be used in a reinforcement learning setting by encoding different kinds of functions that we need in these concepts. And finally, it can also be used as a way to encode trees. And in particular, I showed this example with the Monte Carlo tree search. So these are the persons behind this work. And if there is time, I'm happy to take questions. And I would like to thank you for your attention.